So let's start with the elastic behavior. So strength and strain relation. First of all, let's talk about elastic deformation. Elastic deformation means like when you when you apply the force on an object, if the object goes back to its original position, we call this deformation elastic deformation. So there are four main types of deformation: tensile, torsional, shear, and compressional deformation. So before going there, let's talk about plastic deformation. Elastic deformation, it is reversible, but plastic deformation, it is irreversible. There is elastic limit. Okay, when you pass beyond that limit, the materials will not come back to its original position. So it is going to be deformed like it's going to be plastic deformation over there. So irreversible change will happen over there. Okay. Types of deformations over here, as you see, when you extend an object, in the first shape, on the left first shape, when you check it, like when you extend an object like this, this is going to be tensile deformation. On the other hand, when you play with the shape of the object like this is going to be shear deformation. If there is deformation inside of the object, we are going to call that torsional deformation. Okay, for example, inside of your pen, like when you play inside of the pen or pencil, that is going to be torsional deformation over there. And compressional deformation, on the other hand, when you squeeze a ball, for example, when you squeeze a ball, the ball is going to be compressional deformation. It's going to happen over there. Okay, so the elastic limit depends on the internal structure of the material. Don't forget that. And there is tensile stress. So to find the tensile stress, we are going to use force over area. Force over area. It looks like pressure, but it's not pressure. Okay, don't forget that it's not pressure. It is force over area, but this is called tensile stress. So the unit will be Newton per meter square. The unit will be Newton per meter square. But again, we cannot say the unit is Pascal. Remember, in the pressure, when we divide force to area, we find the pressure. But the SI unit of pressure was Pascal, and we were using, instead of Newton per meter square, Pascal. So in order to not have any confusion, we are just going to use Newton per meter square as a unit of tensile force. So tensile stress. So tensile stress will be depend on the force divided by cross-sectional area of the object. Okay. So to measure how much the copper has deformed, for example, it is not enough to consider just the wire extension. We are going to call the wire extension X. Okay. And to cause a copper wire of, let's say, 10 meter length to extend by 1 millimeter, what can we do? How can we find this ratio? We are going to use the tensile strain. Here we are going to use the tensile strain to find this ratio. So tensile strains mean the amount of extension over the length of the object. Okay, the amount of extension X over the amount of extension over length of the object. So this is going to give us tensile strain. As you see over here, the amount of extension and the length of the object has the same unit. So that's why our object will be unitless. Okay, so object will not have the tensile strain will not have any unit here. It is going to be unitless. All right. So next we have an example over here. Find the tensile stress when a force of 4.9 Newton acts over a cross-section area of 2 times 10 power negative 3. This question I ask you, the solution is over here. Let me give you the solution. So first of all, let's find the tensile stress is force over area. The force is giving us 4.9 and the area is giving us 2 times 10 power negative 3 meters squared. When we divide these two into each other, we are going to find the tensile stress as 2.45 times 10 power 3 Newton per meter square. Okay, this is going to be tensile stress. What about tensile strain? To find the tensile strain, we have length of the object 2 meter and extended by 5 centimeter. First of all, we have to convert centimeter into meter. 5 centimeter means like 5 over 100 meter. That is going to be 0.05 meter. So when we divide 0.05 to 2, we are going to get the tensile strain as 0.025. As you see over here, it doesn't have any unit. Okay, this is tensile strain. We can write this one in scientific notation. How? We can write like 2.5 times 10 power negative 2 in scientific notation for tensile strain. Okay, so let's go to the Hooke's law. Hooke's law, remember that Hooke's law, we learned about it when you were grade 9, Hooke's law. The amount of extension will be directly proportional to the force applied, okay? For example, you apply the force, you're starting from 0 here, you apply the force, and when it reaches a point over here, for example, AB, when it reaches over here, it is going to reach its elastic limits. And when it passes to B, for example, it's going to be deformed, okay? So again, Hooke's law states that the amount of force applied on an object is going to be directly proportional the amount of extension, okay? If you want a more extension, you have to apply more force on an object. So what does elastic limit mean? Let's, like, we already defined it. We said like for each object there is a limit, elastic limit. When you pass that limit, the object is going to be in plastic deformation. So elastic limit means like the point which object is going to come back to its original position or not. Okay, that is the elastic limit for an object. So in the previous graph, when we come to the AB, for example, when we come to the AB, that is going to be elastic limit over there. Okay, when it passes to the B, the object will be in plastic deformation. So yeah, it's going to be in plastic deformation. So it's going to break apart. So limit of proportionality, what does it mean? This means like a point at which extension applied force are no longer proportional, okay? The amount of force that you applied and the extension will not be proportional at this point. Normally, when we talk about Hooke's law, the amount of extension is going to be proportional to the amount of extension. But when you pass this limit of proportion, when you pass a like elastic limit, the limit of proportionality will come up over there. So the amount of force is not going to be applicable for the amount of extension, okay? There is yield point over there. So when there is a sudden increase in extension, we call it a yield point, okay? When there is sudden extension, all right? So let's talk about Young's modulus before talking about Book and Shear modulus. Young modulus tells us like the ratio of tensile stress is going to be divided to tensile strain. Okay. So in order to find a Young modulus, we are going to use this formula. Force times original length of the object is going to be divided the amount of extension times area of the object. So this is going to give us Young modulus. As you see over here, the Young modulus will have a unit of Newton per meter square. How? The unit of force is Newton, unit of length is meter, unit of extension is meter, and unit of let's just do it like this actually. Sorry guys. So let's do it like Newton times meter over meter times area square. So as you see, the meter are going to simplify themselves, so you're going to have the unit of Newton per meter square. Okay, so this is the Young modulus. What about bulk modulus and shear modulus? So bulk modulus tells us like the ability of a substance to resist changing volume when under increasing pressure from all sides. So changing volume over original volume will give us bulk modulus. On the other hand, the shear modulus will tell us the ability of a substance to resist deformation. Here, to resist change in volume, we said here is going to be resist deformation, okay? So it's going to be shear stress over shear strain. We are going to find the shear modulus over here. So what does shear stress and shear strain stands for? Shear stress, again, is going to be like tensile stress is going to be force over area. And the shear strain is going to be, again, amount of extension over length of the original length of the object. So when you divide these two over here, you are going to get like FL over A delta X for the shear modulus. Okay. So we have a energy over here, a kind of energy. when an object stretch, like when your object is stretched, like say when your object a wire, when you extend a wire, the wire will have this kind of energy. Where does this energy come from? It's going to come from you. Okay, the energy that you have due to food, the chemical energy, it is going to be transferred into the wire, and wire will have a strain energy. Okay, so to find the strain energy,
Mr.
we're going to use this formula. Question? So to find the strain energy again, we are going to use this formula: 1/2 times force times x. Okay, 1/2 times force times x is going to give us strain energy of an object. Okay, let's continue. There are two questions over here. I'm going to send you solution them. Okay, let me just skip them. I'm going to send the solution for you. Okay, so fluid statics, the second part of the unit, fluid statics. Let's talk about the pressure due to the fluid column. Remember, when we talk about the fluid, we are talking about gas and liquids, okay? Because both of them can flow. That's why we call both like state of matter, like gas or liquid, as we define them as fluid, okay? So in order to talk about it, let's first talk about the pressure. What does pressure mean? Remember, for pressure for solid was force per unit area. And there was atmospheric pressure, the pressure due to weight of the air, okay? We call it atmospheric pressure. And in order to get the measure of the pressure, we are going to use the absolute pressure, okay? To use the absolute pressure. So we are going to use the absolute pressure. This is defined as force applied perpendicular to a particular area, okay? So this is the absolute pressure. To get the absolute pressure, we are going to use gauge pressure and the atmospheric pressure. Okay, we're going to use the two then. So what does affect the pressure in fluids? Remember, to find the pressure in fluid, we use this formula: height of the column times density of the fluid times gravitational force. So it depends on basically height, density, and depth. Actually, we call it this one depth. This is going to be depth. It depends on depth. It's proportional with depth, density of the object, and gravitational force. So the fluid density is going to be proportional with these three. Okay. Whenever they increases, actually the G is not going to change, but whenever depth or density increases, this is going to also increase the amount of fluid pressure on the object. Okay, let's say you dive 10-meter deep, okay, and you have like 200 pascal pressure on you. When you dive like 20-meter deep, this is going to be double. It is going to be like maybe 400 pascal, 400,000 pascal pressure on you. It is going to be directly proportional with the depth. If that decreases, then this is also going to decrease the amount of the pressure. That's why when you swim, you are going to feel a huge pressure on you. Okay, when you swim, you're going to feel a huge pressure on you guys. So what about Pascal principle? Remember the Pascal principle? Pascal principle was telling us that when you apply pressure on an enclosed fluid, it is going to be transmitted all over equally. Okay, for example, you have a toothpaste in your hand. When you squeeze the toothpaste from the middle, you are going to see that the toothpaste from right and left side are going to be equal. Okay, this is because of the Pascal principle. All right, so there is another question over here. 2 Newton, the force on a brake pedal is 2 Newton, the cross section area of the pedal is 0.05 meter square. If the area of the brake drum is 0.045 meter square, what is the force on the brake drum? So to find this, we are going to divide F paddle, F over A, F paddle over area of the paddle equal to F brake or F drum over area drum. Okay, we are going to use this formula to find the force in drum. So when you crisscross them, you're going to find the force on the brake drum. Okay, you're going to find this one. We are looking for this one. The rest is given you. Just crisscross them and you can find it. Okay, I'm not going to solve it, so you can solve it by yourself. Let's continue. So Archimedes principle. Remember the Archimedes principle? It is about water. It's about the fluid actually. So this principle tells us like the buoyant force on an object wholly or partially immersed in a fluid equal to weight of the fluid displaced by the object. For example, let's say you have a cup of water inside your hands, and you put a like stone inside of the water. The water will displace inside of the cup, right? So this is going to be called, this is going to happen because of the Archimedes principle. Okay, the water displaced is going to be amount of the fluid, displayed is going to be that it's going to depend on the object that immersed or inside of the fluid. Okay, it can be like wholly displaced or like partially, little bit or whole. It doesn't matter. So this is the Archimedes principle. So surface tension and surface energy. So to find the surface tension of a property of a liquid that like the surface that causes it to act like a stretch elastic skin, it is caused by the forces of attraction between the particles of the liquid. Okay, for the particles of the liquid due to force of attraction between them, and the other substance with which it comes into contact. Okay, when it comes to contact with the other object, there is going to be a force of attraction between them. So this is going to cause the surface tension. So the molecules of bulk of the liquid surrounded by other molecules. So all the pulls, they're going to cancel out each other. But you can say that like the surface seem to be like thought inwards. Like this disruption is going to cause the surface energy. So this is going to cause surface energy. So to find the force between the liquids or atoms, like liquids of atom or molecules, we are going to use this formula. Force over length is going to give us the force, the force of attraction between the molecules or atoms. Okay, force over length, the force over length. So let's just we have just two things. We're gonna go over it, and then I'm gonna finish it so we can continue tomorrow. Okay. So pressure difference across a surface field. So to find the pressure difference, we are going to use this formula to find the pressure difference. For this F is going to stand for the surface tension. Okay. Remember, surface tension is force over length or force over area. To find the surface tension, we are going to use force over area. So to find the change in pressure across a surface field, we are going to use this formula. 1 over R1 plus 1 over R2. The R1 and R2 stands for this radius of the curvature. Okay, the radius of the curvature, this R1 and R2 stands for. There are going to be two objects. Yes.
What's R definition?
R, these two R, they stands for radius. Okay, radius of the curvature. Yes.
What's curvature?
Curvature like any object. It could be any object.
Okay.
Okay, but the curvature, like it's going to be circular object. Okay, it's going to be circular object.
So it must have two radius. You mean, right?
Yes. All right.
Okay.
So that's why we call it curvature, right? Okay, so we are going to use this formula to find the pressure difference across a surface field, across like any object. Okay. So what about angle of contact and capillary action? So remember, a liquid cannot exist in perfect vacuum for very long. Okay, a liquid cannot exist in a vacuum place for a very long. So the surface of any liquid is an interface between that liquid and some other medium. So and usually the surface tension between the liquid and the air is greater than the surface tension with the walls of the container. There is going to be an angle between when you apply these two, when these two surfaces meet. So we call this angle contact angle. Okay, where the two surfaces meet, like their geometry must be such that all forces balance. Okay, when these two surfaces meet, there is going to be an angle between them. This angle is called contact angle. Okay, so which is the angle between tangent to the surface makes with the solid surface. Okay, it's going to be a tangent angle. So there's a table in your book, page 172. You can check it out, that table about this contact angle. Okay. So what does capillary action means? Capillary action mean like the movement of a liquid along the surface of a solid caused by the attraction of molecules of the liquid to molecules of the solid. Okay. There is going to be liquid and solid. When they contact each other, there is going to be attraction between their molecules. So we call this action capillary action. Okay. What about meniscus? A meniscus is a curve in the surface of a liquid caused by the relative attraction of the liquid molecules, okay, to the solid surface of the container. So again, there is going to be solid and solid and liquid molecules over here. They are going to be on the surface of the container, and the relative attraction between them is called meniscus. Okay, so capillary action explains two phenomena for us. First one, it explains the movement of the liquids in thin tubes, like not thick, for thin tubes, like small tubes. And the second one, it explains that the flow of liquids through porous materials, such as the flow of water through soil. Okay, it explains this. It explains the action of water through soil. So capillary action explain that. Remember, the soil is solid and the water is liquid. When these two interact, there is going to be a capillary action between them. Okay. All right.